Morning Year 12, what we're going to look at today, just a small little section, but it's going to lay some important groundwork to a big important result that we're going to look at next week. So here is Pascal's triangle. You will know and have seen Pascal's triangle, most recently because of course the coefficients very nicely give us the numbers in there give us the coefficients for the binomial expansions. Of course, to find any one result, we add the two numbers above it. So 10 plus 10 gives us that 20, 56 and 28 gives us 84. There's lots of exciting patterns in there. I mean, very basically, in this diagonal here, we've just got the ordinary integers, but in this diagonal here, we've got the triangle numbers, 1, 3, 6, 10, 15, and so on. We've also got nice results like if we take any two numbers here, multiply 7 by 8, we get double 28, multiply 10 by 11, we get double 55. So there's all kinds of nice patterns inside. To start with this morning, so for your starter, you can choose what to do. I'd like you on your triangle, and note on the second page you have a bigger triangle, so one that goes all the way down to the 24th row. So shade in all the values that are divisible by 2, or divisible by 3, or 4, or 5, or print off several triangles and do all of them. But pause the video and have a shade. Okay, so hopefully you saw just how nice this turns out to be. If we... Sorry, I'm going to be boring and do the twos. I've got 2 there. I've got 4, 6 and 8 there. I've got a 10 and a 10, a 6, a 20 and a 6. Nothing in that row, that's 7s, but here, oh, it's all of those 8s. 36, it's all of these here. I've got a 10, and all of these middle ones. There, and as you go down, oh, I'm having this kind of nice pattern in the middle here. And I formed this triangle. Oh, and actually I've got a triangle up there. I kind of abandon the rest of this row. Look, I've got these 3 here, those 2 underneath, and this one I've got another triangle. Of course it's a mirror image, we kind of know that. I've got an even there, an even there, an even there, an even there. And are there any more? Yeah, I've got a whole bunch here and a whole bunch here. And of course I've just got these in advance. This is, if I was to continue this down to the 24th row, this is what we get for 24 rows. And I know it's essentially all the even numbers, but trying to make it look like number theory. Look, we have just shaded in everything that's congruent to 0 mod 2. And we have these very distinctive triangle patterns formed. If you did mod 3, you would get still triangle patterns, but slightly different. So you can see that you have all of these 3 the same, rather than that bigger one in the middle. If you did mod 4, again, triangle patterns. If you did mod 5, well, what we see so far is what looks like those triangles, all the same size, but of course as we expand, the size of the triangles might be different. The exciting thing about this is this 2 pattern here is a fractal called the Sierpinski triangle, after the mathematician who first discovered it. And the way that it is built up, you draw an equilateral triangle, not really equilateral, but close enough. Join together those midpoints and form another equilateral triangle. If I go to the top one there, I've got an equilateral triangle there, and there, equilateral triangle. So I'm drawing triangles within and then those new smaller triangles that have been formed. And so I would keep drawing triangles again and again in all of these spaces. And of course you can keep doing that. You can keep doing that an infinite number of times, and you get this fantastic triangle shaped pattern here, tried in 3 dimensions there. You can keep doing this indefinitely. It's an example of a type of fractal. Look it up. I love fractals. Fractals are fab. Complex numbers are involved in fractals. You can zoom. You've got this self-similarity and a fairly new area of maths as well. So that is a fractal connected with our modulo arithmetic. We're going to look at a slightly different aspect of our Pascal's triangle. Oh, another exciting thing is, shall I bring this one back? If you find the sum of all of your Pascal triangle rows. So what I'm doing here, I'm adding 1 plus 4 plus 6 plus 4 plus 1. Here, adding this one gets you 32, adding this one gets 64. Of course, what we've got there is just 2 to the power of n for the nth row. So that is another really exciting thing. And of course, there is a reason for that I'll probably mention at some point in the rest of this session. What I've got written down here then, we're particularly worried, or not really worried, but concerned with prime numbers in all our number theory stuff. If you pick out all of the prime rows, so if we look at this one, row 5, so note the top value 1, that would be known as the 0th row. So of course it makes sense to call the 5th row the one that starts with the 5. In the 5th row there, all of those middle terms there are divisible by 5. If we look at the 7th row, I've got 7, 21, 35. All of those are divisible by 7. And of course, it works for the fairly trivial 2 and 3. Doesn't work for the others. So this one is the 4th row. We've got a 6 in the middle. This one, the 6th row. Okay, we've got the 6 there, but all of the other integers, 15 and 20, aren't divisible by 6. 8, that's not divisible by 8. 9, no, 84 is not divisible by 9. So if we keep going down there, they're not all divisible by 10. The next one, where we have this divisibility condition, is the 11th row. 12th row, no, that's odd, can't be divisible by 13. You might not believe me, but check it out. All of those are indeed divisible by 13. 14, 15, no, they don't work. The next one that does is the 17. So you might just want to try those. Try the 19th if you want. But you'll find that the only property where all of the, of course not the ones, but all of the other digits are always going to be divisible by the row number. And of course there's a reason for that. These are all the binomial coefficients. 3 different ways of writing it. The NR, which we tend to kind of write as pure mathematicians. It's kind of, the smallest, takes the less room. NCR, but it is defined as being n factorial over r factorial, n minus r factorial. So that is how we can find each of these. So if we check out a couple of rows in particular, let's look at the 12th and the 13th row. That value there, again, that would be the 0th value, 1st, 2nd, 3rd, 4th. So this is going to be 12C4, and then 13, 1, 2, 3, 4, 13C4. So let's use this to write down the expression and see what's going on. So here's 12C4. 12 factorial on the top, so the product of all the integers from 12 down to 1. R factorial, 4 times 3 times 2 times 1, n minus r, so that would be 12 minus 4, 8 factorial there. All of these n bits, of course, cancel. So there I've got 8 factorial and I've got an 8 factorial there. But I also have some simplification here that I can do. That's 2, I can cancel with the 5, sorry, with the 10 to get 5. That 3 can divide into the 9, and the 4 can divide into the 12. And it's that 4 dividing into the 12, which means that that row isn't going to be divisible by 12, because what we end up with is a 3, an 11, a 5 and a 3. So there's no 12 appearing in there. So what we've got here, that non-prime element, that non-prime value can cancel. That, of course, gets me the 495, which I know is what I have there. Now, look at the difference between that and the 13th row. On the 13th row, so I've got almost the same expression. I've just got, starting with a 13 here, and I've got an extra 9 on the bottom. So everything else is just the same. The 9 to 1 cancels there. That 2 can be divided into the 5 as before. The 3 can be divided into 12, but also the 4 can. That 13 stays there, okay? And because 13 is prime, you're never going to get a 13 on the denominator that divides into it. So that will happen for any prime rows. So for prime rows, this never cancel. And so I'd be left here with 13 times 11 times 5, which gets me 715, but that's not important. The crucial thing is this 13 isn't going to cancel. It's never going to cancel. Here, that 12 can have cancelled. But there, that 13 never can. So we obviously need to think about that, why that's working. It seems to be then, if P is prime, and the row number is less than the prime number, so for example here, that denominator is never going to get up to 13 because R, which is this value here, is less than P. So we always have that number there, R being less than that number there, the value of P. Then we can say that that binomial coefficient, which I'm going to write in bracket form, is a multiple of P. And in particular, we can say that P1, P2, P3, and so on, all the way up to the last one. So this number is increasing all the way up to the P minus 1th one, because P over P would just be 1. They are all divisible by P. Missed off an I there, have I? By P. So, particularly because, of course, we need to relate this to modular arithmetic. PR is congruent to 0 mod P. Now, this leads to the useful result. So, all I've got here is the binomial expansion, and this is the version from year 12, so where you have a plus b to the power of n, where n is an integer. So recently you've done the one where the power can be negative, the power can be a fraction. So here a to the power of p, I've got my binomial coefficients increasing, I've got the power of a decreasing, p minus 1, p minus 2, p minus 3. I've got the power of b correspondingly increasing, ending up with b to the power of p, and I'm just looking at this. I have a feeling that something has gone a bit awry there, hasn't it? So what I should have here, and I will fix it for when I email this to you, it should be b to the power of p minus 1. The power of a is decreasing, so that is just going to be a single power of a. So if you look at all the others, yeah, that 4 corresponds to that, so that 1 corresponds to a power of 1. Yeah, okay, so I must remember to change that. Now, when p is prime then, what's going to happen if I take this modulo p? All of these middle terms here, they're all going to be binomial coefficients, and they are all divisible by p. So they are going to be congruent to 0 mod p, which is where all these zeros here have come from. So that means a plus b to the power of p is congruent to a, ditch all of those, a to the p plus b to the p mod p, which is this result here. So where or why might you be asked about this? So it's basically a stepping stone to what we're going to be looking at next week, but this is a nice result that sometimes comes up. Use the binomial theorem to prove that 2 to the power of p is congruent to 2 mod p. So when we have got a prime power, we're essentially saying that that's just always congruent to 2 mod p. So if we start off with that 2 to the power of p, we need to think about how we can use this expression here. Well, the only way I'm going to get that 2, well, I suppose I could get it by other ways if I'm using non-integers, but by using integers, I can split that 2 into 1 plus 1. And then, depends about the wording here, because this is a prove that, I'm going to do it from the binomial theorem. If it was just to show that or a demonstrate, we might be able to use this result here, but I'm going to go back to this statement up here. But essentially I'm going to use it with 1 plus 1 instead of the a and the b. So using by my binomial expansion, I've got 1 to the power of p plus p1. I'll have 1 to the power of p minus 1 times by b, which is 1, plus p2, and then I'll have 1 to the power of p minus 2 times by 1 squared, and so on. Let's put a few dots. And I'm sure there's lots of you who are thinking, why continue to write? That's just 1 to the power of 1, and then I've got 1 to the power of p minus 1 plus 1 to the power of p. Of course, each one of these powers of 1 is just going to be 1. So on the next line, I'm just going to get rid of all of those individual ones. So I'm now just left with those binomial coefficients. So note, I haven't done anything about the modulus yet. Oh, no, I don't need that power of p. Now I'm going to take my modulus, but firstly I should comment what's going to go on with those here. So I know that all of these multiples of p as p is a prime, and we're not going to have that cancelling happening. So all of those middle terms are divisible by p, so hence 2 to the power of p, which is 1 plus 1 to the power of p, is congruent to 1 plus 0. So I'm just going to spell it out. It's a show that, so let's just put all of those zeros in there, plus 1 mod p. And that in turn, because I've got 1 plus 1, 2 mod p. So 2 to the p is congruent to 2 mod p. So there we go. There's our proof. The next questions involve, it's a little bit more numerical. So you can see that example 2, we have got a fairly low power, 3 to the power of 5 being congruent to 3 mod 5, and we've got a much higher power, 3 to the power of 11 is congruent to 3 mod 11. So here I think it's a show that, it doesn't say prove, and it's an example I've made up. So we are going to say as 5 is a prime number, we can use the result that a plus b to the power of 5 is congruent to a to the 5 plus b to the 5 mod 5. So looking at that and looking at what we're kind of given, that 3, I somehow need to relate that 3 to the a plus b. The most obvious way, so we may not be too sure how things are going to work, but if we write that 3 to the power of 5 as 1 plus 2 to the power of 5, I'm assuming that result. So I don't have to do binomial expansion. I am just going to say, right, that is congruent to 1 to the power of 5 plus 2 to the power of 5 mod 5. And then we just work it out. 2 to the power of 5 is 32 plus the 1. Okay, so that's 33 mod 5. And then we can just work this out. We know that 33 mod 5, okay, that's 30 plus 3. 30 is divisible by 5. So it's congruent to 3 mod 5. So that's all we need to do. I'm sure you will have looked at this in what you did in year 12. But just to show you, if you go to option, and I've lost it, it's in num. Where's num? Math. Okay. Nope. I've lost it. Let's exit. Option, arrow, is it improb? No, it's not improb. Okay. Math. I've just been in there, haven't I? Okay, there is somewhere a button. This is really annoying because it was on there and I went off it. Now I don't want to delete everything. When shall I abandon? Let's try one more time. Option. Is it in calc? It's not in calc. There is somewhere, and it's really, really good. It's under num, which is obvious somewhere. I might try it again at the end, and you can all kind of laugh at me failing again. You type in mod, and then I would do 3 to the power of 5, comma, I want to work it out, sorry, mod 5. So that's what you would type in, and it would just tell you that the answer was 3. Okay, you probably have done that, and Mrs. James has shown you and remembered where it is. Let's continue. 3 to the power of 11 is congruent to 3 mod 11. So what I would do here is say that as 11 is prime, we can use our result that a plus b to the power of 11 is congruent to a to the 11 plus b to the 11 mod 11. Again, 1 plus 2 is what we're going to use. So I can say by that result up there, that's congruent to 1 to the power of 11 plus 2 to the power of 11 mod 11. Now, this is a bit more of a pain, isn't it? Because before, I just knew 2 to the power of 5 was equal to 32. 2 to the power of 11. Okay, so I've got 32, 2 to the power of 5. So I've got 64, that's 6. 128 is 7. keep doubling. 2, 5, 6, 5, 12, 1024, 2048, 6, 7, 8, 9, 10, 11. Okay, so I've got 1 plus 2048 mod 11. Now, you know a test for divisibility by 11, I believe. We can, of course, just easily put that into a calculator, but of course, all these are designed for dealing with big numbers, trying to deal with them without using a calculator. Your test for divisibility by 11, you start with the leftmost digit and you subtract and add in turn. And if that is divisible by 11, this is divisible by 11. And this is going to be -3. So what that tells me is if I'd have subtracted 3 less, it would be equal to 0, and that would be divisible by 11. So, in other words, that's telling me that 2046 is divisible by 11. So, it means that this number here then is congruent to 3 mod 11. And again, the calculator, math, I keep pressing this button and it doesn't get me anywhere, does it? Jump mat. No, that's a matrix. Option. Could it be numeric? Could it be numeric? Yes. Here we go, mod. Type in your mod. I'm dealing with 3 to the power of 11. And I want to check out what that is, mod 11. So that's what I type in. And I get the answer of 3. So do I remember where that is? It was in numeric. Was it in maths? Or was it in mat? Maths, no. No. Okay, I've lost it again. I found it once, never to be found again. Right, the third example, and we're nearly at the end. Sorry for all of this time wasting. This at first, you think, okay, I've got a 14. And a 14, well, it's not a prime number. So what it means is that we can't use this result, but it might still be that if I were to go back and use the binomial, I would show that things didn't, or I would show that things were divisible by 14. The other key thing to spot here is that relationship there. Because I'm going to be looking at things mod 14, I want to show that things are divisible by 14. So think about that 16 there and how it can be split into 14. And of course, it can be written as 14 plus 2. And note that 2 appearing there. Powers of 2 we can deal with easily. So, you know, even though we had a 2 to the power of 11, we could still work it out. A bit of effort, but we could work it out. You know, if that was a 5, if that even was a 3, we wouldn't have been able to deal with that in the same way, or even 3 to the power of 5. So pretty much every kind of power that you have to work out, it will be a 2. And that implies, of course, that these 14s, I'm going to have to work out those powers. If we then use the binomial expansion here, so I will have 14 to the power of 4. I then have NCR, or my first binomial coefficient, which is 4. I've got 14 cubed times by my first power of 2. I've then got NC2, so that would be 4, 2. My power of 14 reduces by 1, my power of 2 increases. I've then got 4C3, 14 to the power of 1 times by 2 cubed, and then that last term is going to be 2 to the power of 4. These here, of course, are 4, 6 and 4. We could just get that from writing down the first few terms of Pascal's triangle. I've got 1, I've got 4, I've got 6, I've got 4, and I've got 1. I don't have to work anything out there because I am about to look at things mod 14. I know that that's got 14 in, that's got 14, that's got a 14, that's going to 14. All of these values here, the 1, the 2, the 3, aren't going to do anything to that. They're not going to divide into that 14. And I mean, I've already said that that is going to be 4. There's nothing dividing into that 14. That's 6. That works out to be 4. So there's nothing at all to reduce those 14s. So I know that all these terms here are divisible by 14. So 16 to the power of 4, which I can write as 14 plus 2 to the power of 4. That is going to be congruent. Well, I've got one 0 term there, another 0 term, a third, a fourth, plus 2 to the power of 4 mod 14. 2 to the power of 4 is 16, and 16 mod 14. Of course, I can just easily reduce that to mod 14. Okay, so can be used not just for primes. If it's not prime, though, you do have to go back and use the binomial expansion. Okay, so questions. Not a huge amount. A couple where you have to do these kinds of calculations here. So worked solutions, full solutions are underneath. I think most of the homework questions, in fact, I think all of the homework questions are going to be on quadratic residues. As I said, this really is just for you to be comfortable with these kind of ideas before we move on to the important theorem next week. Okay, I'll see you next week. Bye-bye.